think so. Okay. So today, so they are mobile in k-space but localized in the real space. So that's why what happens is whether you choose eternal electron model or you choose the localized spin model, they, as far as the spin waves are concerned, the final result, they give the same. There is no change in the result. So you will have magnetization at low temperatures going as Bloch law, following the Bloch law, which is T raised power 3 by 2. Right? So what I am going to do today is just give you a flavor of what spin waves are and what a magnon is, and then talk about the dispersion relation and how do you get the thermodynamic quantities like magnetization, specific heat from those expressions. That's what I am going to do first. If I am left with some time, then I will change gears and go to the indirect exchange interaction. And tomorrow I will continue with whatever is left and along with the magnetic isotope domain theory. Okay, so this probably most of you would have known already, that if I start with a ferromatic chain, one-dimensional chain, then in the ground state, all the spins are in the same direction. It can be either up, down, anything, but we call that as up. Okay? So all the spins are in the up direction, but remember I told you that this is something which you don't have in the books. So to visualize the picture, actually what is happening is that when I say the spins are parallel, they are parallel because it is an axial vector, so at two sides the spins are precessing with the same Lama frequency because they are seeing the same exchange field of all the remaining spins in the system. Okay? So the Lama precession frequency is the same for all of them, and in the ground state, what is happening is that these fellows at any instant of time, if you look at the tip of these vectors, then you find that they are in phase, exactly in phase. At every site, wherever you go, you will find them, they are in phase, exact. That means zero, phase difference is zero. Okay? Now this is happening at T equal to 0, which is the ground state. But once you increase the temperature, then these spins take energy from thermal energy, takes part of the thermal energy, which gets used up in taking them away from this quantization axis, which was there in the ground state. Okay? So this constitutes an excitation because it requires energy to change the orientation of spins from, let us say, Z direction, which was the quantization axis in the at absolute zero. Now, with respect to that, the spins are tilting away from there, and this tilt, extent of tilt, will require that much amount of thermal energy. Okay? So that is the scenario. First, let us start with what happens to the ground state. Okay? So in the ground state, what's happening is that these spins will be all up, but remember they are axial vectors, so they are always having Lama precession. They are always executing Lama precession depending upon whatever exchange field that they see. Okay? So if we consider, let's say, n spins, each of magnitude s, on a one-dimensional chain or ring, the nearest neighbor spins are coupled through the exchange interaction, and delta plus 1, they are the neighboring sites. Okay? And the sum is from delta equal to 1 to n because we have total number of spins is n. Okay? So this is then the angular momentum at every site. If we treat these spin vectors as classical vectors, then in the ground state, this would be just simply, this dot product will be simply s square. So that the exchange energy of the system in the ground state will be minus 2n JEX s square. Right? Now, if I consider the excitation of this system by flipping one of the spins, okay? I flip only one spin out of this whole chain. That is an excitation because to flip the spin, it requires energy. okay, which in this case, let's say, is thermal energy or whatever. So the energy cost that one has to pay in a ferromantic linear chain, if you flip one spin, is this much. Why? Because if you consider these, because the spin pairs that are affected by the spin flip, these are these two pairs, right? One is this pair and there is this one. Before spin flip, this spin was pointing up. So these pairs were ferromantically coupled, and their interaction for these two pairs, the interaction energy was minus 4 JEX S square into N, right? That was this. Two such pairs were there, so that was minus 4 JEX S square for two pairs, right? Now what has happened is after the spin flip, now they are antiferromatically coupled. So now JEX is negative. So the energy cost that you are paying now is for these two pairs, antiferromatic pairs, is 4 JEX S square, right? This is clear. For two antiferromatic pairs, the exchange energy is 4 JEX S square. Earlier, when they had a ferromantic orientation, these same two pairs had an energy of minus 4 JEX S square, right? So the total change in energy that has occurred is 8 JEX S square, right? So that is the excitation energy. That much energy you have to give to flip one spin. Now you have seen that JEX is of the order of some hundreds of millielectron volts, or 0.1, roughly 0.1 electron volt. Okay? It's a huge energy cost that one has to pay to flip one spin in a chain, in a ferromantic chain. Now this cost can be reduced considerably if this change of 180 degrees is equally distributed over all these n spin, total n. We had n spins. All the n spins, if they share this 180 degree phase change, okay, then we will see that I'll repeat it again. What I have shown you is that at the neighboring sites, the phase difference is k times A, and that is constant. Whichever neighboring sites you choose, the phase difference is always Ka. Okay? So basically what is happening is that if you take the two neighboring sites, both the spins are having a Lama precision, and that precisional frequency is dictated, the value of that is dictated by the exchange field, HEX, okay, which I had given you earlier. That is the field that is responsible for this Lama precision. But at a given instant of time, if you look at the tip of one spin and the tip of the neighboring spin, both are constituting this, but if at the same time if I look at, then there is a phase difference between these tips. Phase difference is k times A. Okay? And this phase difference is maintained all throughout the whole chain, ferromantic chain. Wherever you are, the neighboring spins will have this phase difference of k times A. And so that there is a spin wave that travels with a wave vector k, corresponding to a wave vector k, right? But you can excite, in principle, you can excite all these different k values depending upon how much of thermal energy you pump into the system. Okay? So whatever the energy, thermal energy that you put in the system, that is used up in exciting spin waves of different k. At absolute zero, or for temperatures just above absolute zero, it is the long wavelength spin wave that is excited because it requires the least energy that you can see yourself. You just go back on here. If k is 0, okay, then this energy is 0. But if k has a value which is slightly different from 0, okay, then this energy cost is very minimal, is like here. Even if k is now finite, it's not 0, finite, the energy cost is minimal. It's very different, it differs very little from 0, right? So as you increase the thermal energy, now what's happening is that higher, larger and larger k values, or the spin wave modes corresponding to larger and larger k values are getting excited. Till you reach this, it is at high temperatures, where there is a sudden cutoff, okay? And this relationship okay, so this relationship has this form 1 minus cos Ka, okay, at exactly pi, Ka equal to pi, that is pi by A, there you have a first Brillouin zone. So there, now this excitation, as I told you, you remember, if you just recall, in the itinerant electron picture, we had tonal single particle excitations and spin waves. And the spin waves were confined to a very small region in k omega space, that is energy k space. If I take that Brillouin zone, then it was very close to the center of the Brillouin zone. Here, you see, the spin wave excitations go right up to the Brillouin zone. So there is only one type of excitation, which is spin waves, and they can range, their k values will range from 0 to the Brillouin zone value of k. That is pi by A for cubic case. Have quantized amplitude. Okay. So now, if you consider now total n spins, right, that is the maximum value of the spin quantum number. Okay. Now, in the ferromantic ground state, all the spins are parallel, so spin quantum number has its maximum value, n times s. The excitation of a spin wave lowers this total spin because spins are no longer parallel now. Okay? So it lowers this by what? That means if I have only one spin wave of a definite wavelength excited, then it will reduce the spin quantum number from ns to ns minus 1, minus 2. 2 spin waves, minus 2. 3 spin waves, minus 3. So every time you excite a spin wave, it changes the total spin quantum number by 1. If there are n spin waves, then it will reduce it by n. That's what basic message is that. Now let us see whether we have that or not. So this, now we consider a spin wave. I have shown you that this condition is satisfied, V is equal to minus IU, and this relation also is there. So if that is the case, then if we take only the real components, then there is a problem here. This should not be there, minus I should not be there. It is just U sine this, okay? Mark that, it's important. So this minus I is not there, okay? Because if it is minus IU, then that is V, and V and IU are related like this. This I have shown you earlier. Just go back once. Here. This is already here. So this is V because that was minus IU. That was equal to V. Okay? So we have this amplitude. Okay, so now, okay, now what, no, sorry, this is right. I'll tell you why. This is deliberately done. No, I have not put V there, it's just minus IU. It's deliberately done because when you take the real components of this, then the first one would be just simply cos, okay? In the other one it will be sine, real component, right? Okay, so the spin component now has changed this direction from z to the spin component perpendicular to z direction is u, as I told you earlier. That means, this tip, spin tip of the spin changes from this, which was the quantization axis value, and then this changes with respect to that. So this deviation from this deviation, because the spin wave goes like that deviation, that tilt angle, okay, or the tip is tilted from this value, which is at the center now, and the spin is precessing like that. So this tilt from this tip to this tip, that value is nothing but the u. Okay. So then Sz can be given by this, and then substitute for Sx, Sy to get this, and finally for you can write it in this form because this is 1, and if this condition is satisfied, then this is nothing but S minus u square by 2s. That is the Sz component, right? Z component is the component of spin which is along this quantization axis. Okay, so Z component, this is now Sz has this deviation u square by 2s from the S value. S was when there was this quantization axis as absolute 0, all the spins were pointing in a particular direction, and all of them had, so you might have heard of RKKY, any other type of super exchange, double exchange, you've heard of all that. Capital N has only one value. Capital N is the total number of spins. Nk is the number of spin waves of wavelength or k wave vector k. So the spin component, that means the spin quantum number, changes from ns to ns minus nk, right? So now you go back to this, the spin wave of amplitude uk. So we will give you this relation. This is the energy required to excite a spin wave of wavelength or wave vector k. Okay? And you get back that dispersion relation, which is now, this dispersion relation has this form. It is now nk times h cross omega k. Okay? Remember that what is the total spin of a magnon? What is the total spin of a magnon? Yes? What is the total spin of a magnon? 1, right? Understand why 1? Right, plus half to minus half. So this is a boson. Magnon is a boson, right? It has integral or integer spin. It has integer spin. Okay, so it's a boson. So you would have expected that if magnons are bosons, they should obey Bose-Einstein characteristics, right? So that is what happens. You can see it here. This nk is the What is Nk? Nk is the number of spin waves with the wave vector k. Right? So if you now find out what is the average value of Nk, that you do exactly the way you did for average energy. Same thing. Okay? And final result, what you get is this Nk goes as 1 divided by e raised power x minus 1, where x is nothing but, what is x? That is the energy of the wave divided by k beta t. Right? Energy of the spin wave divided by k beta t. So that is this here. You can see yourself. If there is a damping of spin waves that takes place when you go to higher temperatures, closer to Tc, then there will be damping. That you can see in the spin wave resonance, because the line widths would be, this damping will get reflected in the line widths. So you can measure that. But of course, it always is not so easy to separate out various contributions to the line width, because you will have various LLG, damping, and the other exchange conductivity, then other things will be there. So then it's not easy, but in principle it can be done. People have done it in very well-defined systems, which are clean systems. People have been doing. So in principle it can be done. Yes. Yes, they will also contribute. Then you have much wider resonances. So that problem will be there. Inhomogeneities in general, whether it is caused by the RF penetration depth, that means how the thickness of the film compares with the skin depth, that will also decide whether you see inhomogeneous broadening or not. Because as the microwave field will decay exponentially into the film. So if the skin depth is less than the thickness of this, then you will see this magnetization also decaying in the, so there will be this, that will correspond to the resonances at different fields, and so that will add, convolution will be much broader. Okay? So magnetic inhomogeneities, whether they are at the surface, interface, or edges, or actually in the system itself, inherently present, they will complicate things. Okay. We talked about direct exchange. That was the Heisenberg exchange, which was more or less the exchange at the neighboring sites because of the overlap. Because we saw that there is a possibility of the spins interchanging their positions because of the finite overlap of the wave functions at the neighboring sites. Okay, that was your exchange overlap integral. Okay, but it turns out that if you take just only that, if these spins are far apart, then the overlap integral is nearly zero. Okay, so but that does not explain then why a given system should be ferromagnetic, in spite of the fact that the direct exchange does not operate between spins. Okay, now there are three different types of indirect exchange. Okay, there is no direct exchange possible, but there could be an indirect exchange possible. But there are three types of indirect exchange interactions. One is called the RKKY, this is Ruderman, Kittel, Kasuwa, Yoshida interaction. Okay, the other one is the super exchange, Zener double exchange. That is the third one. Okay, so we will see that. RKKY interaction is, by putting it very simply, is that if we are dealing with a non-magnetic matrix which is metallic, and now you embed in that non-magnetic matrix, you embed some magnetic impurities. But the level of these magnetic impurities is very, very low. They are of the order of 1 ppm, 1 part per billion or something like that. That means you hardly have any probability. There is no finite probability for the two magnetic impurities to be close to each other. So there is no possibility of direct exchange whatsoever between the magnetic impurities, which are localized. Okay? So they are localized at some positions within the non-magnetic matrix, and this non-magnetic matrix is like, for example, copper, diamagnetic. That's why we call it non-magnetic. You remember that magnetic and non-magnetic, the difference is that in the magnetic case, if we say something is magnetic, it would mean that there is a finite magnetic moment. And that you will see if it exhibits paramagnetism, then it is magnetic. But if it shows diamagnetic behavior, that means obviously there is no permanent dipole moment, right? There is only a possibility of inducing it by an external field. That's all that you can do. So in the RKK wave, what happens now is that these localized moments, which are localized at some positions in space, are far apart, so that there is no possibility whatsoever of the direct exchange operating between them. Then what's happening is that the conduction electrons of the non-magnetic host, they mediate interactions between these, local moments, magnetic moments, okay, and that is because of the spin of the conduction electron. That means, for example, suppose this was one magnetic moment, the magnetic dipole moment here at this site, okay. Now you have free electrons in a metal, non-magnetic metal, and let's say one of those electrons with a spin is coming like this. Obviously, it cannot approach it if the spins are parallel. So it has to flip its spin if it comes close enough. Then it gets scattered and moves around, goes, if it again sees the other one, other magnetic, localized magnetic impurity, then it tries, this is Z, X, this is Z component, then you would have had Y components and Z components, X components and Y components, right? This is nothing but SI Z, SI Z, SI Y, SI Y, then SIX, SIX. These, now they have been written, this, here you write Z component because it's very easy to operate it. It gives us the eigenvalue as MS, right? That's why Z you keep intact, you don't do anything to Z. But XY components are not so easy because they change the population of spins. You have heard of raising and lowering operators? Right? You have heard of raising and lowering operators. So raising operator means it changes the spin by 1, increases the spin by, and the other one decreases the spin by 1, like that. So these are nothing but S plus, S minus, they are nothing but the raising and lowering operators, and they can be written in terms of the creation annihilation operator. Okay? That probably you have done in a simple harmonic oscillator. Okay? You would have done that. How to write the raising and lowering operators in terms of creation annihilation operators for a harmonic oscillator, that you would have definitely done. So I am not going into that, but just to give you, just to recall, and so that you don't get lost in this. Okay. Now, SZ component is like this. Now, if you look at this form, SZ is nothing but this is proportional to the magnetic moment, right? If I put the magnetic moment at site I would be what? G U beta Si, right? Okay. Now, when I say Z component of this, if you think of applying field in Z direction, just the back of your mind. So what I am doing is that basically it is Understand? Now I wrote in terms of magnetization, which is this G, this mu I divided by the volume of the system, right? That is, magnetization is nothing but magnetic moment per unit volume, right? So I have just written it just to remind you so that you know this, which I have been using, okay? And this is coming because G is 2 and S will have values plus half and minus half. So you are left with only mu V. That is this. This is what we have used earlier. Now look at the thing. N up is what? Is the number operator which spins up. This is number operator which spins down. Right? So that is what you have here. You can see this. Spin up, creation annihilation operator. And same thing at the same site. That is important because we are dealing with this SZ at site I. So it's same site and either spins are up, spins down. Okay, you understood this? So this is nothing new. We know it. Now what is new is this. Okay, so this is how you relate raising and lowering operators with the creation annihilation operator. Here what is happening is the raising means you have to supply some energy. If I have to flip this spin direction to up from up to down,